Yeah, my name is Sheng Wei. I'm assistant professor. I joined ECE last fall. I'm going to talk about immersive mobile video streaming. So before I talk about the project, I want to mention some context why I'm doing this research, because most of my colleagues and students know me as a hardware security person, right? Why I'm doing videos. So actually, these are the places where I have been in the past 10 years. I got my PhD from UCLA and then joined Adobe Research, working for 2 years as a research scientist. And then I became assistant professor at Nebraska for 3 years, and before I moved to Rutgers. At these different places, I formed kind of two lines of research. The first line is hardware security, where I picked up from my PhD at UCLA. And then, of course, I keep doing that until now. So that's the first line. I call it like academia line of research. But the second one is I worked on mobile video systems at Adobe. So then I still keep that line until now. So these are two lines of research, and my hope is that actually at Rutgers, these two lines will meet each other and eventually create a happy ending. But today I'm going to talk about actually the second line of research on mobile video streaming, and I'm going to also touch a little bit on how this can be combined with my hardware security research. First of all about videos, right? We have seen so many different kinds of videos, right? So the most popular one, I guess, is this 2D video that everybody is watching every day, right? From Netflix, you can stream the video on all different kinds of devices to watch it, right? But then the second type of video is this 3D video. We typically see that in movie theaters, right? Unfortunately, it doesn't quite go to the everyone's home, right? We have this theater experience. The third one is actually pretty new. It's called the 360-degree immersive video. Or you can think about it as a kind of a virtual reality environment. So basically, you are sitting in the video. You can actually watch any part of video in the 360 degree by moving your head, just like in physical world, you move your head and see different views, right? So this has become popular. It's actually deployed in YouTube. We have so many 360 degree videos on YouTube now. And then there's the last category, which is emerging. It is so-called volumetric video or 3D point cloud. So basically, in this case, you stream a 3D model of some objects, right, to a video player and display it. So this would enable this AR experience because you can actually do some interaction with this 3D model in the physical world. So this is kind of in the AR space. So today I'm going to talk about my work on the third category, immersive video streaming, and I also have a future plan working on the fourth one. So I'm going to talk about those. So I don't know if I can show this example here. Let me just try. Okay, if it doesn't play, that's fine. I'm just going to talk about this. So this is actually an example video.
The mode, then it might play out of the
yeah, I have to quit.
play mode.
Yeah, maybe I'll just quit and click on here. Yes.
Out of the screen mode.
You need to drag it over to the other screen.
Yeah, I have. There's a link I can click on from here. So then, does it open the browser? Okay, I guess I'll just talk about it then. Don't worry. So the thing I want to show here is actually, this is not a traditional 2D video. This is you're now seeing a 2D view, right? But in reality, if you open this in a browser on YouTube, what you can do is that you can drag your mouse, and then so you can switch to a different view, up and down, left and right, whatever angle you want. So this is if you view it on a computer or on the phone, right? Actually, on the phone, you can even do this motion, right? You just change the angle, and then you will see a different view. And then if you view this video on this head-mounted display device, you can actually move your head and see different views. So that's how this immersive video works. So the challenges here are, let me see if I can. Yeah, the challenges, as you can imagine, right, if you view the video on this mobile device, right, even for this head-mounted display device, if it is untethered, it's not connected to your computer, you have this power issue, right? Because you're actually rendering this huge amount of pixels, right? You have power issue. And then the second problem is bandwidth. So if you stream a 2D, right, two-dimensional version of the video to the device, the video is relatively small, but if you stream a 360-degree, it's 6 to 8 times larger. So it consumes bandwidth. So these are the two problems we're trying to address. So first of all, about power. So before we think about how we reduce power, we should understand where the power consumption is, right? So we did some experiments. This is our power measurement setup. We have this power monitor called Monsu power monitor. Basically, it works like a power supply. You can actually replace your battery on the phone with this power monitor. It supplies this power, and in the meantime, it can tell you exactly how much power that is. So we actually use some 360-degree video with the actual user head movement data set to do a profiling to understand how much power this will consume. But of course, the challenge there is you cannot actually uncover the power consumption of each individual component because you cannot say measure so how much this say screen, how much power the screen is consuming, or how much power this Wi-Fi network communication is consuming. So it's a challenging problem. So we actually did design a set of test cases, right? We kind of do this differential power analysis. You enable some feature, disable some feature, and then you do the subtraction. Basically, you can calculate all of these individual components. So then the results we get is something look like you can, if you look at this, there's a category called VR view generation power. That is actually when users switch view, right? Your mobile device has to calculate, right, which view it should display and then generate the view. For that part, it takes about 40% of the power consumption. And also, you can see the network is consuming a lot of power as well. So based on this understanding, we're aiming to develop a power optimization approach to reduce this major source of power consumption. So the idea, right, is if, say, generating the VR views is consuming power, what we can do is to generate that view less number of times. So that's our first idea, right? We reduce the frame rate. So if before you do the like 60 FPS, if you reduce to 30 FPS, your power can be reduced, right? That's our first intuitive idea. But the problem there is that nobody wants to reduce frame rate, right? If you tell a gamer that you want to reduce his or her frame rate, it's going to be a nightmare. So we cannot just purely reduce the frame rate because of these video quality degradations. So our solution is we kind of try to reduce frame rate at the right moment so that the users won't feel it. So the moment we found is actually during the view switching. This is a pretty unique process only in this VR video streaming, where you switch your head, right? You watch this place, and then you switch to another. During this process, during the switching, you are moving, right? You don't quite pay attention to this part of the video while you are moving. And another thing is that since you are switching, you are more interested in the destination. You're not interested in the source or on the way, right? So you can safely reduce the frame rate during that process. So that's kind of our basic idea in this project as a solution. So then we actually did it, right? So this is a kind of a system architecture. So we have a smartphone HMD. The left part is the original HMD, and then this shaded part, the right part, is a module called QuRate that we developed for this frame rate reduction. So what we did was actually we have to find what is the perfect frame rate that we should reduce to. right? We need to find that with the consideration of this video quality. So we pick up this objective video quality metric, which basically says the video quality is actually dependent on the frame rate, right? And also there are some other parameters like TI or SI or SVQM that are related to motion. So we kind of convert it to the calculation of a frame rate. So frame rate is actually now a function of video quality, right? Then ideally, you can just calculate this frame rate in the real time, right? What is, if I have this requirement for the quality, how much is the frame rate I should pick, right? But it turns out that this computation is very time consuming. If we do this for each every frame, then the video is not viewable anymore. So what we did was actually we did some offline training. Basically, we built this lookup table offline, and then in the online stage, what you do is that you can just find the entry, right, that is closest to your motion, to the user behavior, and then just use that frame rate from the table. So that's what we did. And then we did some evaluation about this approach. The first evaluation we did was actually find out are users really switching their views during video streaming? Because if most users don't switch views, we don't have the opportunity to reduce power, right? So this is the result. Actually, we see that this is the result based on a public head movement data set with 6 videos, and we picked 10 users from that 59 users pool. We can see that most of the users would switch their views more than or around 20% of the time. So that is the opportunity where we reduce the frame rate and save power. So some results, we evaluated power. So maybe the figure is a little bit small, but I can tell you we compare with 2 other approaches. One is actually the baseline, the original video without doing anything. And the other approach is what we call the naive approach, where you just blindly reduce frame rate to the lowest without thinking about whether you're switching or not. And then, of course, our QuRate approach kind of stands in the middle, right? We reduce frame rate during the view switching, so the power consumption is kind of in between of these 2 cases. And then, of course, we want to know whether the quality is impacted, and the result tells us that it's still standing in the middle, right? We are better than the original case, but the quality, of course, is worse than the if you just reduce the frame rate to the lowest, right? Then we actually did some we call it stress test. So you can do power measurement, but eventually maybe you don't trust the result because eventually what people really care about is how long their battery would last, right? So we did this battery life test. So what we did was actually streaming the video all the time, right, from the 100% of battery until the battery drains out. So we can see that from the result, we actually extended the battery life by a significant amount. So that's our results. So the future work on this, right, we just keep looking at this power profile, right? We look at there's video view generation, there is also network power. Maybe we can think about the other components, right, we can reduce. And also looking at this streaming setup, right, from the web server to the mobile device, we are going through this content distribution network and also some edge nodes. So, right, so on these different components, we can do different things to reduce power. So one thing we can do is that on the device itself, we can do some hardware-based approach. So basically do a hardware acceleration, but not only acceleration, but also reducing the power. The second thing we can do is you can offload the video processing task to the edge node, right? So the edge, on the edge, the power is not a concern. So you can actually just stream the processed video views to the mobile device. And the third one is what I'm going to introduce next. Is actually called Viewport prediction. So the idea there is that at any point in time, you are only watching one view. Even if you have a 360-degree frame, you're only watching maybe 60 degrees of it. So what we can do is that if you can predict which view this user is going to watch and only stream that view, right, the amount of video we have to stream will be hugely reduced, and the power will be saved, right? That's kind of what I'm going to talk about next. Are there any questions so far? Yes?
What is your quality measure?
Quality measurement is we have two quality metrics. One is this objective metric I mentioned here called STVQM. That is from the current literature objective metric. The other metric, of course, the ideal quality metric is a subjective metric. So we actually did a user study. We invited 14 users and gave them two sets of videos to watch. One is with this frame rate reduction using our approach, one is without. So they don't notice any difference.
So like I would think maybe if I'm changing direction and you mess up me something, I might get dizzy.
Yeah, the motion sickness is a typical problem in the view switching. But from our user study, in this case, we did not notice that problem. So my thought was that maybe it is because during your switch, right, the view will be blurred anyway. So if you reduce the frame rate of a blurred view, it does not create much impact on the quality. That's what, based on our guessing, we didn't find any problem with the user study that we did. But I think, yeah, I agree, maybe we can do a deeper level study on this user experience. Yes?
So clearly, this is one set of problems with the video, right? What happens if they're playing games, especially multiplayer games?
Oh, yeah. So in this work, we are specifically not targeting on games. Games is a different category because for game, you have very strict this real-time requirement. This will not work for that. For game, you cannot say I reduce frame rate. So the use case we are targeting is this kind of entertainment video. You have a video, right, on YouTube, or you watch some sports game, right, 360 degree. That's for this video streaming, not for game. Yes?
A couple of questions. One is that they kind of leads towards the future direction you talked about, which is that the foveal view is very narrow, the one that's kind of focusing on the point of view that you're looking at.
Right.
So they can be variable type of framing. One that the place where you're looking at high resolution, and the peripheral vision can be lower, and behind can be almost zero.
Yeah.
However, there's some residual resolution needed, because when the switching takes place, the prediction may not be able to immediately have high resolution available, but at least it will display at low resolution. That's
Yeah.
one thought. Second
Yeah.
is that you talked about reducing frame rate and the relationship to the quality, but how about interpolation? Yes, you do reduce it from maybe 60 to 30 frames per second, but you could do interpolation, maybe a smarter way of smoothing out. Any thoughts?
Yeah, I think that's an excellent idea, right? After you reduce frame rate, you can do something else to kind of compensate for it. Yeah, we didn't consider that, but I think that's a clearly a very good idea. But we need to think about like this light-weighted solution, right? So that it's not going to be worse than not reducing the frame rate, right? But I think that's an excellent idea. So for the first comment, actually I'm going to talk about that in the next part, where I talk about view prediction. So basically we will predict the user view for a few seconds. So that, I think that would be a kind of a safe buffer. So we will not experience that you have a sudden change, then something will not show up. So we can discuss more on that next few slides. I'm going to continue with this viewport prediction work. So this is actually, in addition to power, we also want to optimize the bandwidth, right? So the idea, right, opportunity here is that you have a 360-degree view, but at any point of time, you only watch this one small view, right? So if you can predict which that small view is, then you can just stream that part of the video. Or like you mentioned, you can stream this part of video high resolution, the other parts low resolution, right? So that's the kind of the idea here. the problem definition, right? We want to do live streaming. So because the use case for this immersive video streaming, the most popular use case is actually sports games. You watch a game, right? You don't have to be restricted by whatever that camera is facing because you have all the views. You can watch whenever you want. So we target this live streaming case. So live means the event is happening right now. It's not recorded video. It's the real event is happening in the real time. So the problem here is that maybe I can show this. Because of this streaming system setup, so the state-of-art video streaming, right, for large-scale number of users is you do this HTTP-based streaming. So you deploy video as segments, right, video files on the web server, and then the client requests those files one by one, just like it is requesting web pages. So in this way, we can leverage the existing internet, like web browsing infrastructure, and use that to stream video because we have this content distribution network that can deal with the web pages very in a scalable way. So in that case, that means you have to generate the segments of the videos, right? Each segment is a few seconds. So that means you need, if you do viewport prediction, you have to predict for the next several seconds where the user will be watching. Well, a few seconds is not a long time, but if you think about user can move their heads like at any point of time, this a few seconds of prediction is really a challenging task because a few seconds I can move to anywhere I want, right? So that's the challenge here. And then we're looking at these existing solutions. So this is the entire solution space. There's live streaming, and VOD stands for video on demand, that's recorded video streaming, like you watch a movie. And then we're talking about this prediction accuracy. You want to do accurate viewport prediction, right? And looking at existing work, they are mostly based on users. So one line of work is talking about this past user behavior. Basically, you can predict what this user will be watching based on his or her past viewing behavior, right? Maybe he or she is interested in some special part of video, right? So we can use that. You can even do a machine learning, right, and build a model to predict what is the next viewport. So that is one approach. But that approach, like you have to have this historical data about this user behavior, which in this live streaming case, we don't have that because the event is just happening, right? We don't have history data. The other approach, also based on user, is focusing on the current user behavior. Basically, they look at, we call it a velocity-based approach. They look at the current velocity of the user's head movement. And then if the user is moving this way, you can predict that he or she will continue moving this way, continue. So you can do prediction like that. But the problem is it's not going to be accurate. I can show you this example here. So because objects in the video have these many different moving patterns. So you can have, say, only one object moving in one way. So your eye would be just following this object. That we call it one object, one direction moving, one moving. The other case, you have one object. The object can move in different directions, right? N directions. So we call it one N moving. And the other case, you may have multiple objects, and all of them are moving in different directions, right? You don't really know which one to follow or to predict. And then the last one is the most challenging one. So it can be random. So the user can watch anywhere. They just want to look around and trying to locate some interesting stuff. So it can be arbitrary. So in this case, if you think about these movement patterns, this velocity-based approach based on the current velocity will not work, right? Because the user will not actually maintain this direction, this speed, right? So our solution to the problem is we kind of develop on that space here. So we consider both user and video, right? We try to understand user and we try to understand the video content. These two sources of information combined can give us a more accurate prediction. So our approach is the key idea here is we assume that user wants to watch moving objects in the video. So this actually observation is from the sports game, right? When you watch a football game, a soccer game, you want to watch the ball, right? The ball is moving and you just follow the ball. That is what a typical user would do, right? So based on that assumption, what we are going to do here is to track the motion of the objects. So the example here is that we have an original video and then we do a motion detection, try to extract what are the moving objects. And then based on these moving objects, we further select some features from these objects, and then we use computer vision mechanism to track those features. So basically you just follow those moving feature points. And then predict that as your results. So that eventually we can actually predict this kind of viewport, right? Cover these moving objects. So here we applied Gaussian mixture model computer vision techniques to detect motion and track the motion. So the results, we try some videos, test videos from the data set, and then this pink grids you see here are the predicted viewport. You can see it's kind of a subset of the entire view. And the accuracy is this blue bar here is actually our result. We compare with this velocity-based approach and some other combination of existing approaches. We achieve pretty high accuracy, even with the buffer length at 4 seconds, which means we predict the viewports for the next 4 seconds. And then looking at the bandwidth savings, right? Eventually what we care the most is you do a prediction and then you save bandwidth, how much bandwidth you're saving. Here we use this relative percentage of bandwidth compared to the original bandwidth consumption. You can see that in the beginning, right, this yellow line is our approach. In the beginning, we consume a lot of bandwidth is for the initialization. And then after initialization, it will drop to around 20 to 40% of the bandwidth. So that is the, some examples of our results. So the limitations of this approach, right, if you rely on motion, one problem is that this motion detection is not perfect. So in the video, if the camera, right, is moving, that means if the camera is moving, that means from the view of the computer vision approach, right, everything is moving. Then you would identify every object as a moving object. Then it doesn't make sense to make prediction. You predict your predicted view is the entire view, right? So the other problem similar to that is if the background is moving. For example, if you have like some tree in the background, maybe the tree leaves are moving because of the wind, then you would identify that background as a moving object and predict that. That would be wrong, right? So, and the third one is we kind of build the assumption that people only want to watch moving stuff, which may not be true for some videos. In some videos, maybe people will watch these static objects. In that case, this motion-based approach will not work. So our solution is that let's try to understand better about this user behavior, right? Where exactly users want to watch. So, so the key idea here is that we think user may want to watch meaningful objects. So not just moving objects, but meaningful objects. So we try to identify the semantics of the objects. We did some experiments here, like we try some example, right? We identify the objects. There are like 3 people here, player A, player B, player C. And then there's a surrounding, right? Not the object. There's also the surrounding area, which takes a large spatial area. But we identify that the users spend very less time, even the size of that object is big. So the user's interest is not focused on like the physical size of the object, but focusing on the semantics of the object. So based on this idea, we actually developed this semantics-based viewport prediction. We detect objects in the video and then try to track those meaningful objects so that you predict that as a viewport. And then of course we get some better results than the motion-based method because when the video seems dynamic, the motion-based method does not work well. So I think I have a limited time here, but I will just talk about some future, very briefly, future direction on this. We have done motion-based detection. We have done this detection based on these meaningful objects. And the future work is we keep extending our assumption, right? People may not want to only watch this meaningful object. Sometimes it's not object. It's kind of activity or action in the video. We call it the region of interest. And also sometimes there's audio that can help with the video. Eventually we will try to build this framework where based on the video and user, we select what is the best signal from the video that we should leverage to build this prediction framework. So the very last slide is about future work, right? On the fourth category of video, this 3D point cloud video, volumetric video. So we identify this security problem there, security concerns, because now if you stream a 3D model of a real person, right, to another person, if that person is not authorized to see this 3D model, there may be security or privacy concerns. One example is that it may break this Face ID detection. You have a very high resolution model of a user's face, then you can use that to bypass this Face ID based authentication system. So that's kind of a security problem we try to work on. And the solution is not that straightforward. One solution is that you encrypt the video. But this video is huge. If you do encryption, the overhead is too much. So what we are thinking about is that we can do actually opposite use of adversarial attack. Basically, you can change this 3D model a little bit so that the user will not see the difference. But somehow it can not bypass the Face ID detection system. So you change the model a little bit and then it won't go through the Face ID detection. So that's kind of our future work, trying to do some, connect this to the security domain. So yeah, I think that's all. I would appreciate our sponsors, and also all our projects are released on this GitHub repository. Thank you.
Question.